And so we're still in vibrational spectroscopy, but this is the Raman methods, or inelastic scattering. And so we're in the visible region of the electromagnetic spectrum, but we're using the scattering of those visible photons to capture the vibrational information in the mid-infrared. And so we'll talk about dispersive spectrometers, or using them in the Raman setup, and then we'll look at the different transitions that we have. So we have several lasers that are at our disposal. We have like a 633 nanometer laser. That would be like a helium neon laser, pretty common. 785 is a real common diode laser. We have a neodymium YAG laser, ND YAG, which is a neodymium atom inside a crystal of yttrium and aluminum. So yttrium and aluminum crystal, they're oxides in a garnet crystal structure. So yttrium, aluminum, garnet, that's YAG. Let me go ahead and do this on the board. So this is a very, very common laser system. So the garnet is the crystal structure. Yttrium and aluminum oxides are the elements in that structure. So you can make a pure crystal of yttrium and aluminum in the garnet crystal structure. And then you can dope in, take out some atoms of yttrium and put in some neodymium atoms. And you can vary that concentration quite a bit. So you dope it with a little bit of neodymium. And so the neodymium atom is doped into this structure. And it's the energy levels of the neodymium atom that cause the laser. So we can hit it with a flash lamp, cause a population inversion, and then stimulated emission will produce a coherent beam of light. And that beam is at 1064 nanometers. And that's in the infrared. So we could do spectroscopy with that directly, but it's not really tunable. It's just stuck at 1064 nanometers. And so if you're going to do a spectrum, you need to change the source. You need to scan the source somehow. So it's really difficult. But we could use it for Raman, bounce it off a substance, and the scattered photons can give us information about the vibrational spectrum, okay, the vibrational motions. But still, using infrared gets us into the problem of having to use salt for our windows. So we'd like to get this into the visible. There are certain crystals that have what they call nonlinear optical properties. So you send in 1064 light, and the electron cloud oscillates at twice the frequency, or half the wavelength. And it will spit out photons that are half the wavelength. And so you can send this through a frequency doubling crystal and get 532. So that's doubled frequency, or half the wavelength of the 1064. And that's a green laser. And that's what we have in our Raman setup. This also gets you really into the mid-range of the visible light detectors. And so all of our CCD cameras and technology that we've made for photography can be used now to do spectroscopy. And so that's come down in price, because if you think of all the camera that you have on your phones and everything, I mean, that technology is mature and cheap. And so these spectrometers are really cheap now. The laser is pretty expensive. That's probably still the most important, or the most costly thing, is getting the laser and the nonlinear optics for doubling that signal, or doubling the frequency. And so this 532 nanometer laser is what we have in our spectrometer. Now this is Raman, not Ramen. So I see this in your reports occasionally. It's not the noodles, okay? And so this is Sir C.V. Raman, won the Nobel Prize in 1930. He used sunlight and filters and looked at this box with the sample in it. I forget what sample he used, but he could see red scattered light in this box, and there was no red photons coming in. So he had a blue filter. He passed blue light into the box and saw red light coming out. And so he documented this and was the first to observe this effect, and so it got named after him, the Raman effect. This is me in grad school. This is our laser, okay? So you've seen our little tiny laser that we have. This power supply next to me looks like about the size of a washing machine, and it was full of capacitors and power circuits. And it ran this flash lamp laser here. Or actually, I'm pointing to the output. So 1064 nanometer lights coming out, and also 532. This was a Q-switch laser, and so it would build up the population inversion and throw out any photons that happen to be happening spontaneously until we wanted the stimulated emission event to happen. And then it would dump all of that energy out in 10 nanoseconds. So that's a very short time window. It was only millijoules, but when that few millijoules came out in 10 nanoseconds, that if you were there at that 10 nanoseconds and you were a molecule, you felt megawatts of power. So megawatts is like power plant sized electric fields. And so these molecules were feeling 10 megawatts of power for 10 nanoseconds. But that's enough time for them to scatter the light and do the Raman effect. So we got very sensitive Raman spectroscopy in 10 nanoseconds. And so there was a lot of circuits that we used to time our detectors. So the detector only looked for 10 nanoseconds, got the light, and then turned its eyes off so it didn't get saturated with the noise from the room. But these 10 nanosecond bursts of light were about 10 feet long. And so you could actually time your experiments by sending light back and forth on the table and get all your beams lined up at the same time. And it's pretty cool. A nanosecond of light is about a foot long. So if you had a nanosecond pulse, it would be about a foot long. And you wouldn't see it because it's so fast. I mean, you'd have to use some sort of detector to detect it. Okay. You see it bouncing off the optics. Now the modern Raman, this is similar to what we have. We have these little handheld fiber optic Raman spectrometers. It's a 2-photon process, as we just took a Kahoot. We have the Rayleigh scattering on the left, which is much more probable. So you see a lot of green light. Then we had the Raman effect. We have Stokes shift and anti-Stokes shift. Now we have the possibility for all of these, for all 3n-6 vibrations, if the symmetry allows. So you can do those Raman selection rules, and they're based upon the polarizability operator. So for IR, this middle piece from the character table was X, Y, and Z. But for Raman, it's all of the two second order combinations. And some character tables will have X squared independently, then Y squared and Z squared. But then other character tables will have these combined. It just depends upon the point group. Sometimes you see things like the X squared minus Y squared. So that also counts. Okay. Sometimes you see X squared plus Y squared. Sometimes you see 2Z squared minus X squared minus Y squared. So that's another combination that you might see. But all of those we would use in the Raman selection rules. So anytime you have a second order X or Y, then you have that.
And get those from the character table?
Yes, so on the right of the character table, you have all of those things with Rx, Ry, Rz, those are the rotations. Straight X, Y, and Z, those are the polarized light that we would use. And these are the polarizability functions, the combinations of X's and Y's. So whenever we're coming up with Raman selection rules, these are the things that we would use. And if you look at anything that has an inversion center in the character table, you'll see that the Raman ones are all at the top half of the table where I is +1, the character under I is +1, and then the IR ones, X, Y, and Z, are in the bottom half of the table where I is -1. Now here's the same kind of diagram we had for the Raman spectrum, but for the IR spectrum, but this one's for Raman. Again, we have our four states at the ground level. the ground state here where all four vibrational quantum numbers are 0. We have this 0, 0, 0 transition, which really isn't a transition, but that would be Rayleigh scattering. So this would be called the Rayleigh line. So that Rayleigh line is really strong. We use filters to kind of keep that out of our detector because it would blind the detector. You turn up the sensitivity of the detector and then you flash a laser in its face, it's gonna temporarily blind the detector. It's very similar to what you see at night when your eyes are adjusted and a car turns on its headlights. You're temporarily blinded, and that happens to the detectors as well. It can actually damage them too. Then we have the new 1 transition. So this is the quantum jump and vibration quantum number 1 and 0 for all the others. And so you would label this one new 1, the next one new 2, new 3, and new 4. Now, why are the intensities the way they are? So you're like, new 4 is such a tiny one, and new 3 is tiny, and new 2 is huge. That's that transition moment integral. So when you took the wave functions for the ground state and the excited state and light and integrate that over all space and square it, you get the probability of that event happening. And so there's something about nu 2 that's more probable than all the others. It scatters more photons on average than all the others do. And so infrared intensities are based upon the change in dipole moment. So if I've got that CO2 molecule and I have the carbon in the middle and the oxygen's here and that carbon's oscillating left and right, this is a molecule that doesn't have a dipole moment until it starts to vibrate. And so that's a huge change in dipole moment. So that's a huge intensity in the infrared. For the Raman, it's the size of the electron cloud. So we're talking about the polarizability of the electron cloud around the molecule, and if something can make that cloud bigger and smaller, that's a huge change in polarizability. The cloud's getting more diffuse and flexible, or tighter and smaller and harder. And so it's changing that electron cloud size. So in benzene, what do you think is the largest peak that you could have? Whatever vibration could make the cloud change the most. Think about the benzene ring. If that ring breathes and gets bigger, that pi cloud gets bigger. And if that ring shrinks, that pi cloud gets smaller. So that's the largest scattering vibration in benzene for the Raman. Is the CC stretches, all 6 of them, symmetrically expanding and contracting. And because the whole cloud is oscillating, it can oscillate with light and scatter those photons very efficiently. And so that's what we see with the benzene. If you've got some kind of motion that really doesn't change the size of the electron cloud, it's probably not going to scatter very well, and you'll have a small peak. So, if the ring's just deforming like this, so some bonds are stretching and other bonds are shrinking, but the size of the cloud isn't really changing, it's going to be a pretty weak peak in the Raman. Yeah. So this is sort of a cartoon of what's going on. The laser hits the sample, light goes everywhere. Most of the green light goes back into some beam dump. We throw it away. We just put it into a piece of metal because we want to manage the heat. We got a lot of photons. And so we just dump it into a piece of metal, put a fan on it, and let it stay cool. And then we send the scattered light, typically at 90 degrees, so we don't deal with this major piece of light here, and bounce it off a prism and hit a diode array. So the green line here is our Rayleigh line. That's most of the light that comes out. But then over here, shifted from that Rayleigh line is our Raman shifted light. That's the vibrational spectrum that we get. Here's a little bit more accurate picture. We have a 532 laser coming in, fiber optic, hits the sample inside our little black sample holder, absorbs all the light. We don't have to see it. We're not exposed to the laser light or anything like that. Goes back through the same fiber optic, but down here there's like inside there's multiple fiber optics. One's with the incoming laser and one's with the light that it's detecting. And so we've got different fibers in that fiber optic cable. And so then the signal fiber optic goes into our spectrometer and gives us our spectrum. Yes?
How do the other signals have, since it's scattering, how do the other signals have oscillate? You collecting the
Yeah, so we're throwing away a lot, okay? And so it would be nice to try to collect that. And so some little more fancy spectrometers will put mirrors here. So they'll put this in a reflective cup. So that light bounces off and goes back this way. And then it'll put, it'll kind of, think about a parabolic reflector, where that is the center of that parabola. You can do it like a semi-spherical cup here, or you can put it in the center of a parabola so that all that light comes out and is collimated. So there's a use of your geometry. Remember back in the day, taking the sort of center burst and collimating the rays on a parabola? You can do that with this and then have collimated light coming out the bottom. And then it's still pretty spread out. And so then you use telescopic optics, like a telescope, to take this collimated light that's this big and shrink it down to collimated lights that's this big. So you can use Cassegrain optics to tighten that beam and get it onto your spectrometer. Yeah.
Focus it.
Yeah, so focus it, but also get it tightly collimated so that it can hit the grating collimated and come off dispersed. Yeah, and so then that's where the cost comes, because these optics are all reflective and they, they got to be precise. So the precision of the optics will really jump up the cost. That might be a $300 or $400 little collection piece, or depending on the company, maybe $3,000 or $4,000. Some of them are proud of their optics, and maybe rightly so. So there's some sample calculations at the end of this PowerPoint that you can do that are also related to the lab, but we're pretty much out of time. But this is sort of working through some simple problems. If the incident line is 532, what's the actual wavelength of light that's been scattered at 3,000? Okay, and so this is a simple calculation. You first convert 532 to wave numbers, subtract 3,000 from it, and then convert it back to nanometers. And then you can see it's still visible light. So it still goes through glass, still is detected by our camera optics, and so on. So.